This is a calorimetry problem, just like what we've done in the laboratory, where we mix two chemicals, here ammonium bromide and water, and the temperature changes, and then based on all of these observations, we're supposed to calculate the enthalpy. So that's the question. Find the enthalpy of something. What's enthalpy of something? Enthalpy of something is what we call delta H, and it's always something that we represent by a reaction equation. And when we do the reaction equation, the delta H is related to it in terms of the moles of everything in the reaction equation. Okay, that's where we have to get to. Now, what information are we given? We're given information about grams. We're given information about grams here. This is different substance. This is water. We have a temperature change right here. We have a calorimeter constant, which is like a specific heat, except that's for the whole calorimeter. So that's the 1.55 joules per degree Celsius. And then we have a specific heat. So let's remember what kinds of problems we have in thermochemistry and what types of relationships we have between the substances or the factors that I've just described. Here we have delta T. We noticed we had a change in temperature. Anytime you have a change in temperature, you're going to be doing a problem like these ones here outlined in blue, in which you take the temperature change and the specific heat times the mass, and you get heat. So these three things will multiply together to give us heat, which is joules. You can see how the equation works down here with the units given. You have joules equals joules per gram per change in temperature in Celsius. That's joules per 1 gram per degree Celsius. And the grams multiplies by grams, the degrees Celsius multiplies by degrees Celsius, and they cancel out. So you end up with joules, so that's heat. Well, we can get there, you can tell from the kinds of things in the problem, specific heat and delta T. But where do we want to go? We want to go to a delta H. And to do that, we're going to need moles of the substance that's involved in the reaction. Let's do the first part first, the part that's outlined in blue, and we'll come back to the last part afterwards. So here we're going to do the first section, temperature change. Temperature change is 23.01 minus 20.31, or 2.70 degrees Celsius change. What underwent that change? Remember that our relationship is going to be the heat change of the solution. This is what this is. The solution drops heat change, Q, is going to be equal to the specific heat of the solution, which is right here, (4.18 joules per. Now remember that per degrees Kelvin is going to be the same as per degrees Celsius in terms of change, which is what we're dealing with here. The change in Kelvin is the same as the change in Celsius. You're going to take that times the mass of everything. Where's the mass? The solution is a combination of the solid and the water. So the mass is going to be 6.32 plus 105.80. And then you're going to multiply by the temperature change. So it's going to be times the 2.70 degrees Celsius. You can see that the degrees Celsius will then cancel. This here is grams. The grams will cancel, and we're left with joules, which is the unit for heat. So that gives us the heat change of the solution. Anything else change temperatures? Well, they give you information here about the calorimeter constant of the coffee cup. That's the 1.55 joules per degree Celsius change. So there must be some heat that we're supposed to consider, some heat change that's due to the coffee cup. The coffee cup has the solution in it. It starts at the same temperature as the water that was in it, and presumably goes down to the same temperature the water had been at the end. So the delta T here would be the same as that of the solution. Let's write an equation for the heat change of the cup. To do the heat change of the cup, we're going to use the calorimeter constant. This is the joules needed to change the whole cup 1 degree Celsius. So you don't have to multiply by grams here. This is for the whole cup. You just multiply by the number at the bottom, that thing. So you have to multiply by the change in degrees Celsius, which was the same as the change in degrees Celsius for the rest of the solution. So your heat change of the cup, the heat change of the solution, is the heat change of everything that we see here. All of this heat must go into the calculation for the enthalpy. The total heat change is the total of these two. If you multiply all of these together and add them up, you get that the total heat change is 1,269 joules. Now that we know the heat change of the solution in the cup, let's go back and find the thing that is supposed to be solved for in this problem, that is the enthalpy change. Remember that delta H refers to some process that can be expressed as a reaction. Dissolution means the same thing as dissolving, so the enthalpy of dissolving of ammonium bromide would be simply ammonium bromide solid. Remember, we always have to put the phase signs in here, going to ammonium bromide aqueous. That's all. That's very simple. And the delta H is what goes with that reaction. Now let's quickly look back. Our temperature had dropped in this process. So if the temperature of the solution drops, when the solid dissolves, that means that the process we've just written as an equation here is what? Exothermic or endothermic? It's endothermic, and the sign that goes with that for the delta H is plus. Now I point that out here because I'm not following the sign convention all the way through the problem. I'm just going to use my logic to get the sign right at the end. And my logic is that this has got to come out to be an endothermic reaction because it's making the solution drop in temperature. Remember what the delta H units are. Enthalpy units are supposed to be in kilojoules per mole. As you look at this reaction, that makes sense. It's going to be kilojoules, and this reaction reads 1 mole of ammonium bromide solid goes to 1 aqueous. But the number we have, 1,269, is first of all joules, so we might want to change that to kilojoules. And it's joules per how much? It's not joules per 1 mole. It's joules per, in terms of amount of ammonium bromide solid, 6.32 grams. But we need this in units of kilojoules per mole. So what do? Grams to moles. Here's your molar mass, 97.94 grams per mole. And this is of the ammonium bromide. So when you multiply this out, you see grams ammonium bromide cancels grams ammonium bromide, and you're left with the units of kilojoules per mole of ammonium bromide. When you multiply and divide this out, you're going to see that you have 19.7, and remember the sign, we just said that it was endothermic. Always put the sign if you have a delta H, just so everyone is clear that you looked and you figured out whether it was plus or minus. So that would be our answer.